Welcome to Space Talk. I'm your host Rifat Bari, Harvard exoplanet researcher and former AI researcher at the Marlins Lab and perfect ACT scorer and CCNY BS in physics candidate. I'll be your tour guide for the inner solar system, the four inner planets, Mercury, Venus, Earth, and Mars, that make up the rocky planets. We're going to be taking a look at the composition of these planets, how long a day takes, how long a year takes on each of these planets, their distance from the sun, and how their surface topography looks like. So if you want to join me in for this ride, let's take a look at the inner solar system. Today, we're going to start with the first planet, the scorchingly hot Mercury, with an orbital period of only 88 days. Let's take a look at Mercury. Here it is. Clicking on Mercury, and there you go. You can see just how close it is to the sun in this interactive visualization. So Mercury is a bit boring, right? It's a pockmarked surface. It's almost like our moon. It's about the same size as our moon, just a bit bigger. And it's about 40% the size of the Earth. And so you can see Mercury in its full glory over here. Let me go ahead and see if we can reveal some details about Mercury here. So first of all, if you look at the internal composition of Mercury, you're going to see that it's kind of like most of the rocky planets, right? Mercury has an internal composition of an inner core that's made of some molten iron perhaps, and it's made out of a crust that has silicate rocks in it. So if I look at the structure of Mercury, you can see that right here. You've got that inner core, that molten core right there, and you've got that silicate crust over here. And Mercury, even if it had an atmosphere when the solar system was forming, that atmosphere would have been long gone because this thing is way too small to have the gravitational pull to keep an atmosphere. And of course, as you might expect, Mercury is scorchingly hot, but it is not the hottest planet in the solar system. That honor belongs to Venus. But let's take a look at some actual pictures from Mercury. So if you look at the surface of Mercury, you can see that much like our moon, its surface is pockmarked with craters. And those craters are a representation of just how old this thing is. Right? If you look at Mercury over here, let's see, take a look at these next images. So these are from NASA's satellites and robots that went to Mercury and took pictures. As you can see, this picture is taken from a flyby of Mercury. As you get near the surface, you can see these kind of craters, and these craters are a signature of just how old the planet is, right? So the more craters, the older the thing is. Here you can see that some of the craters, they actually leave this kind of an interesting shape. So if you look at the formation of craters on Mercury, let's bring this to our side here. The craters, of course, they're going to leave this kind of bulge, but the craters also have some kind of some of the craters have a ripple effect, right? You'll have some kind of a dot sticking out from the center. You can see something like that over here. The reason why is that much like when you drop water into an ocean and that water initially kind of jumps up and then causes that ripple effect, you can see that kind of same thing happening with an asteroid impact or whatnot. So let's erase that over here, clear the canvas, and I'm going to delete this pen. And so let's see if we have any more images of Mercury. Here you can see Mercury, more of its craters. It takes only 88 days for Mercury to go around the sun. So believe it or not, you'd live up to your 328th birthday if you lived on Mercury. So that's Mercury. Let me go ahead and zoom out over here. Let's see if we can take a look at some of the stats of Mercury. So you can see the distance of Mercury from the sun is about 58 million kilometers. Its radius is about 40% of Earth's, right? So it's about the size of our moon. You can see this is Mercury's mass. It's very, very light, not very dense. And so yeah, here's Mercury's gravity. It makes sense that Mercury's gravity is a fourth of what our gravity would be, right? 0.4 of what our gravity would be, because it's a fourth of Earth's radius. And you can see the length of a year on Mercury is only 88 Earth days, but a day on Mercury takes 59 Earth days. So that's kind of wacky right there. And you can see Mercury actually has the greatest change in its surface temperature compared to any other planet. So you can see over here the surface temperature of Mercury fluctuates between 800 degrees Fahrenheit during the daytime and minus 300 degrees Fahrenheit in the nighttime. So that's a temperature variation of almost 1,000 degrees. Venus beats the top temperature for Mercury by 100 degrees. So the surface temperature on Venus is about 900 degrees Fahrenheit. Venture out to the next planet after Mercury, and that's going to be Venus. Now Venus, despite the fact that it's referred to as Earth's sister planet, it doesn't look like Earth at all, right? And you can see that right here. Venus has the same size as Earth almost. It has around the same mass. But as you can see, the surface looks nothing like Earth. Now, maybe it's not clear from this picture right here, but Venus has a thick atmosphere. And that thick atmosphere causes a greenhouse effect. So let me illustrate what's happening on. So let's get our pen working here. So if I get a picture of Venus facing our sun, let's go ahead and see. Okay, so there's the sun. And let me go ahead and illustrate why Venus is the hottest planet and not Mercury. So you have sun rays, you have the sun radiating solar energy, right? And that solar energy, of course, comes to Venus, right? But Venus has something that Mercury doesn't have, namely it has this atmosphere, this thick atmosphere. And what this atmosphere does is it kind of acts as a blanket. So it takes this incoming solar radiation and it's going to trap that incoming solar radiation. So this solar radiation is going to almost act like a billiard ball in a pool table. It's going to be bouncing around and it's going to get stuck. It's going to be inside. It's going to remain within Venus and it's going to heat up Venus's surface temperature to almost 900 degrees Fahrenheit. Okay, Mercury, on the other hand, doesn't have that, right? Most of the solar radiation that hits Mercury, it doesn't get absorbed in the same way that it gets absorbed in Venus, because Venus has that greenhouse effect. In fact, many astronomers call this a runaway greenhouse effect, right? This is what would happen if you have too many greenhouse gases like carbon dioxide or methane in your atmosphere. This would be the result. So this is almost like a horror story, right? If climate change went crazy, maybe this is what we'd end up with. On the other hand, many astronomers also believe that Venus might have been in the past an abode for life when its atmosphere wasn't so crazily trapping in heat from the sun. But nowadays, you know, it's there's no hope. But recently, astronomers have detected a bit of phosphine in Venus's atmosphere. So it could be that life cannot survive on Venus's surface, but it can survive in Venus's atmosphere. We'll just have to wait and find out. When NASA sends the Da Vinci missions to Venus, we'll just have to wait and find out what the results are. So that's Venus for you. Let me go ahead and X out of this. Let's see the internal composition of Venus. If I go ahead, click this eye over here. Okay, so Venus, as you can see, Venus is, by the way, the brightest planet in the night sky. After the sun sets, you can see Venus in the night sky. And let's take a look at its composition. We expect pretty much the same thing as most terrestrial rocky planets, right? You expect a molten core, you expect a silicate crust, and that's indeed the same patterns we see on Venus. If you want to take a look at our stats here, Venus is, remember Mercury was about 58 million kilometers. Venus is about twice that at 108 million kilometers. If you have any questions, by the way, put them down in the comments below and I'll be sure to address them. Venus, its radius is about 95% of Earth, as you can see right here. Very close to Earth, that's why it's called our sister planet, although it doesn't look that way. Its volume is 88% of Earth's. Its mass is also close to that. Its gravity is, 90% of what we have here on Earth. The length of Venus's year is 225 Earth days, which is not bad. But a Venus day is actually longer than a Venus year. If you look at this right here, that's crazy. That means a day on Venus takes longer than a year on Venus. Day on Venus takes 243 Earth days. So that's pretty wacky. And if you look at the surface temperature here, hopefully you can see that that's almost 900 degrees Fahrenheit. Hopefully I can get some pictures of Venus up here. Okay, wow, this is great. So these pictures were either taken by the Soviet landers, that 2 Soviet probes that landed on Venus, or NASA's missions. I'm not quite sure which ones, but you can see here all of this data we have about Venus. First of all, I do believe these are topographical maps. These show you the elevation of Venus's surface, red being very low terrain areas, blue being normal elevation. Let's see what other pictures we can see of Venus. You can see Venus has this kind of yellowy texture to it, and it's also pockmarked with craters and whatnot. And so that's, if I take a look at this picture, I believe this is showing elevation data. So that gives you a kind of idea of the topography of Venus. So that's Venus. Let's go ahead and see if I can zoom out Venus. Okay, we're zooming out. And so that's Venus. Now we're going to go to our home planet, the third terrestrial rocky planet, and that's the Earth. So okay, so this simulation actually shows all of the satellites orbiting Earth in very high resolution. So let's take a look at the Earth. So the Earth, there's so many interesting things to talk about, but I think one of the most important things that I'll mention is the carbon silicate cycle. So what is that? The carbon silicate cycle. This cycle, plus the fact that Earth is in the habitable zone from the sun, makes it possible for Earth to be an abode for life. If you look at Earth, it has our Luna. This is our moon, and Earth, it has the biggest moon with respect to its host planet. So the ratio of the moon's radius to the Earth's radius is the biggest, right? So hopefully you understand what I'm saying. The moon is the biggest satellite around its host planet compared to Earth's radius. Okay, the moon is, the Apollo missions landed on the moon. We landed on the moon first with Apollo 11 in 1969. The historic footsteps of Neil Armstrong and Buzz Aldrin are still on the moon because there's no weathering or anything to erode those footsteps. And you can just see how pockmarked the surface of the moon is. It's amazing. It looks surreal. But the thing is, we only see the near side of the moon, right? Because it's tidally locked to the Earth. If you wonder why, it's because of the gravitational dynamics between the moon and the Earth. But the thing is that we only see the near side of the moon. And when the pictures of the far side of the moon were actually taken, it was amazing because it turned out that the far side of the moon doesn't have as many craters as the near side of the moon. And now you might ask the question, why? Well, that's exactly what NASA is trying to figure out. Why the far side of the moon doesn't have as many craters as the near side. Could it have to do something with gravitational deformation? Maybe because the near side is always close, is always being tugged by the Earth. Could be. So let's see what info this simulation gives us about the moon. So, okay, and also the simulation mentions that the moon is in fact drifting away from the Earth at about 4 centimeters a year. Hardly noticeable, but perhaps an interesting fact. So the moon is about, talking about stats and facts, the moon is about 250,000 miles away from the Earth. James Webb is going to be 4 times that distance, just to give you an idea. And on the moon, you have a sixth of Earth's gravity. So let's see what pictures we can see. Oh, okay, so this is the famous Earthrise picture. So if you don't know the context behind this picture, one of the Apollo missions took a picture. One of the astronauts saw the Earth rising on the moon's horizon, just like the sun rises on Earth's horizon. And he thought that it was a kind of brilliant juxtaposition of what the Earth looked like from the moon and what the sun looks like from the Earth. And so this picture is famously called Earthrise, as a testament to that fact. Let's see what other pictures we can see. This is obviously this right here. I don't think this is a real picture. The reason why is because when you take pictures from the moon, one of the common criticisms is, why don't you see any stars in the night sky? And the reason why is because the exposure time of the camera blots out all those stars in the night sky, so you don't see them. And of course you can see these crazy big craters on the moon. And the Eagle, Apollo 11's Eagle lander landed on Tranquility Base, right? So that's near one of the craters of the moon. Here you can see the American flag in the distance. So all of these are amazing pictures of the moon. If I'm not mistaken, this could be the this could be the far side of the moon, which doesn't have as many craters. Okay, so that's the moon, our one and only natural satellite. Oh, great. Now we've got the weather ads. That's our moon. Now we're going to go to the last terrestrial planet, and that is Mars. If I can get Mars in the simulation, that would be a miracle. By the way, these little pock marks you see here, that's no bug. This is the asteroid belt between Mars and Jupiter. So let's see where Mars is. Mars is kind of far. If I remember, it's about 158 million miles away from the sun, as opposed to 93 for the Earth. So okay, this is Mars. It's not very high resolution in the simulation, as you can see, but Mars is a very exciting place because it could have in the past been an abode for life. You can see it has two natural satellites, Phobos and Deimos, hardly bigger than my pinky finger, but that's beside the point. One of the interesting scars you'll see on Mars is this amazing kind of valley right here, this kind of scar. Let me notate that actually. This actually has a name. Let's see if I can, right here. This valley is called Valles Marineris, and so the hypothesis is that this little valley could have been weathered and wedged by water that used to once be on the surface of Mars. But of course, all that water has been obliterated ever since Mars lost its atmosphere. And Mars lost its atmosphere because, first of all, it doesn't have that gravitational tug that Earth has to keep on its atmosphere, but also because of that crazy intense solar radiation from the sun that's constantly bombarding Mars. So Mars does still have a very thin atmosphere. It's a thousandth the thickness of Earth's atmosphere, but it's practically negligible unless you're actually landing on the Martian surface. So let me erase this canvas right here. So that's Mars for you. Let's see if we can look at the ice caps of Mars. So here's one of the ice caps, as you can see. It's covered in natural ice. So when I say ice, there's actually many different kinds of ice. There's high pressure ice, there's ice 1, ice 2, ice 3. Ice 1 is the one you're probably most familiar with. It's the ice that we experience here on Earth. The other ices form under very high pressure. So this ice in Mars's polar caps is mostly ice 1, the ice that we know and love. And the reason why polar caps like this could be interesting is because they can help regulate the environment. They can help regulate the sustainability of a planet if that planet has an atmosphere or something like that. But keep an eye out on those polar caps. They could be interesting. So now, as you know, first of all, NASA has an infatuation with Mars. It's been sending rovers to Mars, Curiosity, Spirit, Perseverance, so many that it's pretty hard to name them all. Let's take a look at the composition and some photos of Mars. So, and this caption here reminds me that Mars has the largest mountain in the solar system, obviously bigger than Mount Everest, and that kind of makes sense because Mars has a lower gravity, so it can't pull in those hedge spikes as much as Earth can. So that mountain's name is Olympus Mons. Maybe we'll get a picture of it somewhere here, but first let's look at the composition. We'll have a silicate crust and a molten core. Let's take a look at these pictures of Mars. So that shows quite prominently Valles Marineris. And here you can prominently see these ice caps, these polar ice caps. You can see the Martian rover being one of NASA's rovers being powered by that solar panel. And what else do we have here? This could have been an ancient riverbed. And so yeah, those are some pictures of Mars. And so that's it for the inner planets. So I've talked a little bit about, and maybe we can get a close-up of Mars's two natural satellites. Here's Phobos. You can see there it is, Phobos, and not much to say there. And here's Deimos. That's Deimos. And so those are the four inner planets. As you can see, they're mostly small, they're mostly rocky. You're actually not going to notice the same pattern in other solar systems. Other solar systems have Jupiter-sized planets close to their stars, but somehow our solar system was conjured in just the right way so that the small rocky guys are on the inside and the big gassy guys are on the outside, and they're separated by this asteroid belt. So folks, that's it for the inner solar system. Tomorrow we'll check out the outer solar system, Jupiter, Saturn, Uranus, and Neptune, and we'll check you out in that episode. So stay tuned for the next episode of Space Talk, and we'll see you tomorrow.